Welcome! In this session, we'll be exploring an interesting problem, problem number 766, Toeplitz matrix. We'll break it down step by step, understand the intuition behind different approaches, and discuss the trade-offs in terms of time and space complexity. Let's dive in. In this problem, we are working with a Toeplitz matrix. A matrix is considered Toeplitz if every diagonal running from the top left corner to the bottom right corner contains the same elements. This means that for any element in the matrix located at position matrix I, j, it must be equal to the element found at matrix I plus 1, j plus 1, provided that both indices I plus 1 and j plus 1 are still within the matrix boundaries. Your task is to write a function that checks whether a given matrix meets this condition and returns a Boolean value, true if the matrix is Toeplitz, and false otherwise. The input will be a 2D list of integers representing the matrix, and the output should indicate whether the matrix satisfies this property. Let's look at an example to better understand the concept. Suppose the input matrix is a 3x4 grid like this: 1, 2, 3, 4, 5, 1, 2, 3, 9, 5, 1, 2. If we examine each diagonal, we can see that the diagonal starting from the top left corner, containing the elements 1, 1, 1, has the same value throughout. Similarly, the diagonal starting from the element matrix 0, 1, which is 2, gives us the values 2, 2, which are also consistent. This pattern holds for all the diagonals in the matrix, meaning every diagonal contains identical elements. Now, continuing with the first example, the diagonals containing 3 and 4 are also consistent, as each of these diagonals contains identical elements. Therefore, this matrix satisfies the conditions of a Toeplitz matrix, and the function should return true. Let's consider a different example: 1, 2, 2, 2. Here, the diagonal starting from the top left corner gives the elements 1, 2, which are not the same. Specifically, the element matrix 1, 1 is 2, which differs from the starting element matrix 0, 0. This inconsistency means the matrix is not a Toeplitz matrix, so the output should be false. With the second example, we concluded that the matrix was not Toeplitz due to inconsistent diagonal values. Now, let's explore another case. Consider a 1x1 matrix, such as 7. Since it contains only one element, there are no diagonals to compare, and it trivially satisfies the Toeplitz matrix condition. Therefore, the function should return true. Moving on to constraints, the matrix will always have dimensions between 1 and 20 for both rows and columns, and every element in the matrix will be an integer between 0 and 100. Finally, let's discuss some edge cases. For a single-row matrix, like 1, 2, 3, 4, there are no diagonals to compare, so it always qualifies as a Toeplitz matrix, and the output is true. Similarly, for a single-column matrix, such as 5, 6, 7, the same logic applies, and the output is true. On the other hand, a matrix like 1, 2, 3, 1 does not satisfy the Toeplitz condition because its diagonals are inconsistent, so the output is false. Lastly, if all the elements of a matrix are identical, for example, 8, 8, 8, 8, then all diagonals will naturally have the same value, and the function should return true. These special cases help clarify how to handle different inputs while solving the problem. To understand the Toeplitz matrix problem, we can first consider a brute force approach. The intuition is straightforward: we directly check all diagonals in the matrix to ensure that every element along a diagonal is identical. A diagonal is defined as a set of elements where the difference between their row and column indices remains constant. For example, if the top left element of a diagonal is matrix I, j, then each subsequent element in that diagonal must satisfy the condition matrix I, j, equals matrix I plus 1, j plus 1. The steps for this approach are simple: start from the top left corner and, for each element, compare it with the next one in its diagonal. If we find any mismatch, we return false. Otherwise, after checking all diagonals, we return true. While this method is easy to implement and works well for small matrices, it becomes inefficient for larger ones due to the repeated checks for overlapping diagonals. The time complexity is O(m*n), where m is the number of rows and n is the number of columns, and the space complexity is O(1), since no additional memory is used. Now, we can explore a more optimized approach. This solution takes advantage of the Toeplitz property, where the condition matrix I, J, equals matrix I1, J1 must hold true for all valid pairs of I greater than 0 and J greater than 0. What this means is that we don't need to check every diagonal explicitly. Instead, we can simply compare each element with its top left neighbor. Starting from the second row and second column, we loop through the matrix, and for each element matrix I, J, we compare it with matrix I1, J1. If we find any mismatch, we return false. Otherwise, if all comparisons pass, we return true. This approach is efficient because it avoids redundant checks, ensuring that each element is only examined once. Like the brute force method, the time complexity remains O(m*n), but the optimized approach is far more efficient in practice due to its reduced number of comparisons. Additionally, it maintains a space complexity of O(1), since no extra data structures are needed, making it suitable for both small and large matrices. Although the optimized approach is efficient, it can be slightly less intuitive for beginners compared to the brute force method. As an alternative, we can consider a different strategy that uses a hash map to track the first element of each diagonal. The key idea here is that diagonals in a matrix can be uniquely identified by the difference between their row and column indices, I, J. Using this property, we initialize an empty hash map, where the keys represent the diagonal indices, I, J, and the values store the first element of each diagonal. For every element matrix I, J, we check whether its diagonal key I, J exists in the hash map. If it does, we compare the current element with the stored value. If it doesn't, we add the current element to the hash map as the first element of that diagonal. If we encounter any mismatches during this process, we return false. Otherwise, we return true. This approach has the same time complexity of O(m*n), as we still iterate through all elements, but it requires additional space proportional to the number of diagonals, which is O max m(n). The hash map-based approach has its own advantages and disadvantages. One clear benefit is that it works particularly well for sparse matrices, where most of the elements are zero or where the matrix dimensions are uneven. By tracking only the first element of each diagonal, we can reduce the number of comparisons in certain scenarios. However, this approach also has significant drawbacks. First, it requires additional space to store the hash map, which can become impractical for dense matrices or very large matrices with many diagonals. Additionally, the use of hash map lookups introduces a slight overhead compared to the optimized approach, which does not require any extra data structures. Overall, while this method is a creative alternative, it is generally less efficient than the fully optimized approach for dense matrices. Among the three methods discussed, the optimized approach stands out as the best choice for this problem. It strikes the ideal balance between simplicity and efficiency. By focusing only on adjacent elements in each diagonal, it avoids unnecessary checks for overlapping diagonals, resulting in a time complexity of O(m*n) and a space complexity of O(1). The brute force method, while easy to understand and implement, becomes inefficient as the matrix size increases due to its redundant operations. On the other hand, the hash map approach, though useful for sparse matrices, introduces extra space overhead, which is unnecessary for dense matrices. The key insight that makes the optimized approach so effective is the realization that the Toeplitz property depends solely on the relationship between adjacent elements in each diagonal. This eliminates the need for iterating over entire diagonals or using additional data structures, making it not only efficient but also elegant. The trade-offs are clear. The optimized approach is faster than brute force and more space efficient than the hash map method. In conclusion, the optimized approach is the most efficient and elegant solution for verifying whether a matrix is Toeplitz. By leveraging the relationship between adjacent elements, it minimizes redundant operations while maintaining clarity and simplicity. This makes it suitable for matrices of all sizes, as it achieves a time complexity of O(m*n) and a space complexity of O(1). While other approaches like brute force or the hash map method have their own merits, they either lack efficiency or introduce unnecessary complexity. The beauty of the optimized approach lies in its ability to solve the problem in a straightforward yet highly efficient manner, making it the clear choice for this task. In this problem, we are working with a 2D matrix, and our goal is to determine if it is a Toeplitz matrix. A matrix is considered Toeplitz when every diagonal running from the top left to the bottom right has identical elements. To solve this, we start by understanding the key property of a Toeplitz matrix. For any element at position matrix I, j, the one directly below and to the right, matrix I plus 1, j plus 1, must have the same value. Mathematically, this means all elements along the diagonal share the same I-j value. Next, we iterate through the matrix. We exclude the last row and column from our checks because those elements do not have valid diagonals below or to the right. This ensures that we only focus on elements that can be compared to their diagonal neighbors, reducing unnecessary computations and keeping the algorithm efficient. For each element in the matrix, we compare it to its diagonal neighbor, specifically matrix I, j, with matrix I plus 1, j plus 1. If we find any mismatch during these comparisons, we can immediately conclude that the matrix is not Toeplitz and return false. However, if the loop completes without encountering any unequal pairs, we return true, indicating that the matrix satisfies the Toeplitz property. Additionally, we handle edge cases. For example, if the matrix has only one row or one column, it is trivially a Toeplitz matrix because there are no diagonals to check. From a performance perspective, the time complexity of this algorithm is O, m asterisk n, where m is the number of rows and n is the number of columns. This is because we check approximately m1 asterisk n1 elements, skipping the last row and column. The space complexity is O1, since all checks are done in place without using additional memory. The key insight behind this algorithm is that the Toeplitz property depends entirely on adjacent diagonal elements, specifically the relationship between matrix I, j, and matrix I plus 1, j plus 1. This means we do not need to track or explicitly store all diagonal elements, which helps eliminate redundant computations. By limiting our checks to just these adjacent elements, we achieve a highly efficient solution. For edge cases, such as matrices with a single row or column, the property holds by default since there are no diagonals to evaluate. The algorithm operates directly on the input matrix, which is represented as a 2D list, and no additional data structures are required. To illustrate, the Python implementation provided demonstrates how to iterate through the matrix while comparing each element to its diagonal neighbor. If a mismatch is found, the function immediately returns false, otherwise, it concludes with true, confirming that the matrix is Toeplitz. This concise and efficient approach ensures correctness while maintaining optimal performance. This Python implementation checks whether a given matrix is a Toeplitz matrix. The function isToeplitz matrix takes a 2D list, matrix, as input and returns a Boolean indicating whether the matrix satisfies the Toeplitz condition. First, we calculate the number of rows and columns in the matrix using the len function. This is necessary to know the boundaries of the matrix for iteration. The algorithm then iterates through the matrix using two nested loops. The outer loop runs through all rows except the last one, range, rows 1, and the inner loop runs through all columns except the last one, range, cols 1. This ensures we avoid accessing indices outside the matrix when checking the diagonal elements. Inside the nested loops, we compare each element matrix, R, C, with the element diagonally below and to the right of it, matrix, R plus 1, C plus 1. If any such pair of elements is not equal, the function immediately returns false, indicating that the matrix is not Toeplitz. If the loops complete without finding any mismatched diagonal elements, the function returns true, confirming that the matrix is Toeplitz. This solution efficiently checks the Toeplitz condition in O, m asterisk n, time, where m is the number of rows and n is the number of columns. The algorithm is straightforward and avoids unnecessary computations, making it suitable for large matrices. This is the Java implementation for LeetCode problem number 766, Toeplitz matrix. The logic mirrors the Python solution, where we iterate through the matrix, excluding the last row and column, and check if each element is equal to the one diagonally below it. Key differences in Java include explicit type declarations for variables and arrays, as well as the use of standard Java array syntax. The solution ensures clarity and correctness while adhering to Java conventions. To solve the Toeplitz matrix problem, we start with a basic example where the input matrix is a 3x3 grid. First, we initialize the dimensions, the number of rows is 3, and the number of columns is also 3. Now, the goal is to iterate through all elements of the matrix, except for the elements in the last row and the last column, because those elements don't have diagonals below them. Starting with the outer loop, we begin at the first row, row 0. Within this row, we enter the inner loop, which starts at the first column, column 0. Here, we compare the current element, matrix 0, 0, which is 1, with the element diagonally below right, matrix 1, 1, which is also 1. Since they are equal, we continue to the next column. At column 1, we compare matrix 0, 1, which is 2, with matrix 1, 2, which is also 2. Again, they are equal, so we finish checking all columns for the first row. Now, we move on to the next row. In the second row, row 1, we repeat the same process. Starting at column 0, we compare matrix 1, 0, which is 4, with matrix 2, 1, which is also 4. Since they are equal, we move to column 1. Here, we compare matrix 1, 1, which is 1, with matrix 2, 2, which is also 1. Again, they match, so we complete the checks for the second row. Since we have now checked all rows except the last one, and all diagonal comparisons have been consistent, we can conclude that this matrix is a Toeplitz matrix. The function would return true as the final result. Now, let's look at an example that is not a Toeplitz matrix. In this case, the matrix is still a 3x3 grid, and we follow the same initialization process with rows equal to 3 and columns equal to 3. For this new matrix, we begin with the same approach. Starting at row 0, column 0, we compare matrix 0, 0, which is 1, with matrix 1, 1, which is also 1. These values are equal, so we move to column 1. At this column, we compare matrix 0, 1, which is 2, with matrix 1, 2, which is 5. Here, we find a mismatch, as 2 is not equal to 5. Since the Toeplitz matrix property requires that every diagonal is consistent, finding just one mismatch is enough to determine that this matrix is not a Toeplitz matrix. Therefore, the function immediately returns false without proceeding further. This demonstrates how the algorithm can efficiently exit early when a mismatch is detected. Next, we'll examine a simpler edge case, a single-row matrix. In the case of a single-row matrix, the dimensions are initialized with rows equal to 1 and columns equal to 4. Since there is only one row, there are no diagonals to verify. The Toeplitz matrix property is inherently satisfied here because there are no diagonal elements to compare. As a result, the function directly returns true without performing any further checks. This highlights how the algorithm handles edge cases like single-row or single-column matrices. In general, the key observations from our solution are that the algorithm iterates through all elements except those in the last row and column, comparing each element with its diagonal counterpart. If a mismatch is found, it returns false immediately, otherwise, it returns true after completing all comparisons. Edge cases are handled seamlessly because no comparisons are required when there are no diagonals to check. The time complexity of this solution is O(m*n), where m is the number of rows and n is the number of columns in the matrix. To understand this, let's break it down step by step. First, the outer loop runs through all the rows, excluding the last one, which means it iterates m1 times. For each of these rows, the inner loop iterates through all the columns, excluding the last column, resulting in n1 iterations per row. Within these loops, the algorithm performs a single constant time comparison between the current element and its diagonal neighbor. When you combine these loops, the total number of iterations becomes m1 asterisk n1. Since constant time operations dominate within the loops, the overall time complexity simplifies to O(m*n). This remains true in the best, average, and worst case scenarios because the algorithm always checks each element, excluding the last row and column, no matter the input. The space complexity of the solution is O(1), which means it uses a constant amount of additional memory regardless of the size of the input matrix. Looking more closely, the algorithm does not create any new data structures such as lists or sets that would require additional space. The input matrix itself is not modified, so no extra memory is allocated for it. The only additional variables used are the loop variables, like r and c, which are simple integers and take up a constant amount of space. Because there's no memory usage that grows with the size of the input, the space complexity remains constant, making it highly efficient in terms of memory usage. When we compare this approach to a brute force solution, the efficiency becomes even more apparent. A brute force method would involve explicitly checking each diagonal of the matrix one by one. With a total of m plus n1 diagonals and up to n elements per diagonal, the time complexity of this approach would be m plus n n, which is significantly less efficient than the m n complexity of our optimized solution. The reason the optimized solution is better is that it minimizes the number of checks by systematically comparing only the necessary elements, those in the first m1 rows and n1 columns, to their diagonal neighbors. This ensures we achieve the minimum number of operations needed to verify if the matrix is Toeplitz. In conclusion, the solution is optimal in both time and space complexity, achieving m n time and 1 space by efficiently iterating through the matrix and directly comparing diagonal elements without requiring additional memory. When solving the Toeplitz matrix problem, there are a few common mistakes that you should be aware of. First, not handling edge cases for small matrices can lead to errors. For instance, assuming that all matrices are at least 2 by 2 might result in incorrect handling of 1 by 1 or even empty matrices, which are trivial cases but must still be properly accounted for. Another frequent mistake is using incorrect diagonal indexing logic. The relationship between row and column indices, represented as I, j, is critical for identifying elements along the same diagonal. Miscalculating this relationship, for example, confusing I plus j with ij, can completely break your solution. Lastly, it's important to avoid ignoring out-of-bound indices during traversal. This is especially problematic in non-square matrices where boundaries are uneven. Failing to account for these edge cases could lead to runtime errors or skipped elements during validation. Next, inefficiency is another pitfall to watch out for, particularly when working with large matrices. Using a brute force approach with n squared, or worse complexity might seem straightforward but can fail performance requirements as input sizes grow. Instead, aiming for an optimized n plus m solution is essential. Another mistake is overcomplicating the solution by introducing unnecessary data structures. For example, storing entire diagonals in temporary lists or dictionaries may seem helpful, but it often increases both time and space complexity unnecessarily. This approach adds overhead without solving the problem more efficiently, so keeping the solution clean and minimal is key. To excel in interviews, it's crucial to recognize the fundamental insight of this problem. All elements on the same diagonal share a unique property: the difference between their row and column indices, or ij, remains constant. This simplifies traversal and validation significantly. When discussing approaches, balance simplicity with performance. While brute force may be easier to implement initially, it's important to highlight optimized solutions that leverage the problem structure. Additionally, interviewers often explore follow-up questions, such as handling rotated matrices, extending the problem to 3D arrays, or finding the longest valid diagonal. Optimization techniques like using a hash map to store diagonal values can further minimize redundant computations and demonstrate your ability to think critically about space and time trade-offs. This problem also connects to several other matrix-related challenges on LeetCode, which can help you practice complementary skills. For instance, Toeplitz matrix itself is a direct application of diagonal consistency checks. LeetCode 73, set matrix zeros, shares similarities in careful traversal and in-place manipulation of matrix elements. LeetCode 54, spiral matrix, involves traversal strategies for 2D arrays, which can enhance your understanding of matrix operations. Finally, LeetCode 498, diagonal traverse, focuses on diagonal traversal patterns, making it an excellent follow-up to solidify your grasp of this type of matrix traversal. Finally, let's discuss some alternative approaches and their trade-offs. One optimized method uses a hash map, where the diagonal index, ij, is the key, and the first element on that diagonal is the value. This allows you to validate each diagonal efficiently with a time complexity of n plus m. The trade-off here is that while this approach is faster, it introduces a small amount of additional space complexity. On the other hand, in-place validation eliminates the need for extra data structures by comparing elements directly during traversal. This minimizes space complexity to 1, but it can be trickier to implement and debug, especially for edge cases. Lastly, there's the brute force approach, which involves explicitly extracting and comparing all diagonals. While this method is easy to understand and implement, it becomes impractical for large matrices due to its n² time complexity. Choosing the right approach depends on the problem constraints and your priorities for efficiency versus simplicity. Great job following along. To recap, we explored the Toeplitz matrix problem, discussed key concepts, and reviewed the complexity trade-offs. Remember, practicing matrix-based problems builds a strong foundation for more advanced topics. Keep coding, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!